My name is Fabio Bonsignorio. I am the CEO and founder of a small robotics company called AI and Robotics, and I am a professor in the Institute of Biorobotics of the Scuola Superiore Sant'Anna in Pisa, in Italy. So the purpose of this short talk is to give you some novel idea about what could be a paradigm change in robotics. I mean, everybody dealing with these problems know that while robots are today a really established part of manufacturing scenario, for instance, you cannot even think of building a car without using a robot. Actually, the issue of passing from the shop floor in the factories to everyday tasks, or also to simulate behavior very similar to the human, or even to an insect-like intelligence, has proven to be extremely difficult. And we have a question that we may ask ourselves, which is, should we? What's inside so in Europe, it's very popular an approach which is called cognitive science to robotics, or cognitive robotics. The sensible question is, does this imply something different from the current paradigm of robotic research? Because if you think about, and we will enter a bit more into this. For instance, I will give you more detail. For instance, we can easily spot that most of the robotics research assumes that you have a Cartesian division between body and mind. Could this affect the real possibility to obtain the kind of functionalities that we expect from a robot? Someone thinks so. And then a very short caveat, which is, of course, what I'm going to say, it's typical of a specific point of view. So there are many people working in this direction, as there are many people working in a different direction. I really like this book, which is from the middle of the 19th century and was written to help expeditions into the Far West. Because in the very first years of the exploration of the Americas, many of these expeditions were lost. And so the American Army commissioned to this captain, which was an expert of the Far West, an handbook to give advice of how to really not being lost. And what I really like is this fact that the first in the foreword, he warns the readers that, of course, every people giving you advice on how to reach the Far West have interest, have bias, and this also applies to research in robotics, AI, and cognition. So, of course, depending on the approach that you may have had in the latest 20 years, you probably tend to interpret things in a way or the other. And this also applies to what I'm going to say. And of course, just the idea of building robots is actually extremely old. I mean, already in the Greek mythology, they were talking about robots. Now, for instance, Hephaestus had assistants which were mechanical and we were doing everything. Maybe more interesting, and it is interesting if you check the original text of Greek text, that actually Aristotle already thought conceptually of what a robot could be, And actually, if you look at the real translation, he assuming already that a good working as robot assistant, what in modern time we were, should have some capability to anticipate and to understand what's going on. No? So it's not that. And then really, I mean, don't start from a big bang, but just a bit closer to us. So actually, kind of mechanical automatas are not typical of our age. So already, in particular, this is a very probably the oldest example, which was not surprisingly in China, in some 4,000, almost 5,000 years ago, which is a kind of a mechanism which produces a behavior which you could interpret from your intentional. So if you do an intentional stance, you may interpret as alive. No? And then, much closer to the current approach, already in the Hellenistic age, they built automatas where the computing part was performed by a clock. So a clock can be, you know, the typical Babbage computer, no, was a mechanical mechanism. So it was an automaton to do calculation. It was implemented in, with a mechanical structure because this was what available at the time. And this actually produces some very nice examples, and then I will come back on this later. Then, let's say, and after a long, you know, there was a long interval. After a long interval, this idea of automata was taking again forward, and always it was implemented by mechanical computers. But it's interesting to here we don't see very well, but this automaton of the end of the 19th century actually were humanoids, and they were extremely realistic. No? So, for instance, this writer automata, which is now in Neuchâtel Museum, it was actually able to write different. With lever pen, was able to write short sentences of about 40 words. So, and then there are other example in Japan. The real, of course, like in many other things, the real change was when the microprocessor was available. Because when the microprocessor was available, there was no conceptual change. But the number of states of a computer implemented automata are much more than that of a mechanical system of gear and clutches, and this was the big change. And this is just to say that actually the current, when I say today, it is a kind of must-have. For instance, if you want to build cars or washing machine, to have robots in the line. But the kind of technology that it is used, it's currently the mainstream usage in industrial robotics is based on these ideas from the 50s. So it's something which is 60 years old, 50, 60 years old, and the conceptual setting is actually thousands of years old. So there is no, if you look at some, so this is like the one of 50 years ago. But more generally, if you think in terms of these robots, what you really conclude is that they are close relatives of the Swiss automatas or the Karakuri dolls. So essentially what you do is that you have a mechanical structure, and separated from it, you have a computing state automata. So you have something that, according to an algorithm, is able to do different things, but without a capability to react to the environment. And this, then of course there are mixed, so by now there are different kind of humanoids, for instance, today, no? Which, as I told, they are an evolution of other kind of humanoids which we have had before, but so they are much more complex. You may do some distinction. For instance, the ICAB, although it has a structure which is essentially the same of the Asimov, it is not. It's more focused not on the mechatronics, so on the management of the movement, but it is focused on the cognitive capabilities, still maintaining this difference in between the body and the mind. So let's say someone think, I for sure share this idea that this could be, and yeah, this is kind of provocation, no? Because I say, okay, but already 5 centuries ago there was very nice humanoid dolls built with this approach. Today, of course, we have the Ishiguro's androids, but the point that we raise it, that they say, remember the initial caveat, could be right or could be wrong, is, are we sure that we can really obtain something which is able to manage an open-ended environment? Because this is the problem. If you focus to the kind of robotics system which have been so far developed, they are very good if they are teleoperated, and they are very good if they are closed into a factory and someone has decided what they can meet. No? Which kind of events can occur in the robotics lifetime. But if you put them in the wild, or even in a room like this, you immediately have serious problems. So we don't have solution really well. So the point here of this, which is told, is of course a biased standpoint. My standpoint, the standpoint of many people actually in the robotics community, especially in Europe and Japan, is that in this direction we cannot do very far. So that this could really be a roadblock, which is not due to the fact that we have to add more technology, no? Because the alternative point to this point of view is no, it's not a paradigm approach. It's not a matter of how approach the design at the basic level. It's that I need more technology, faster computer, better actuators, better sensor. And if I put more and more stuff like that, finally I will get what I want. The idea that I'm pushing here is different. I don't think it's a quantity. It's also a matter of complexity of technology, but still probably is not there. Also in terms of computing capacity. But might also reside in the fact that animal intelligence is different. So, for instance, if you think these are quite much more simpler humanoids than the humanoids like Asimov, which is, if you want, the top of technological approach. They have a difference yet. They are not fully actuated, so not every joint is directly actuated, but they are passive, meaning that essentially they explode the natural dynamics of a physical structure. The intriguing observation that you can do is that while a robot, fully actuated robot, well optimized, well engineering, like Asimov or Curie, I mean any of these one, even the better, have a power absorption which is about 20 times the one that we have to work. So we work with about 5% of an energy used by one of those robots. The interesting point about this kind of robots based on passive working is that they consume more or less 1.5 the energy that we consume. They have yet a problem, which is, and this has led to some new design, like SH robot, no? or Roboi. Where is the problem? That this kind of passive worker have a kind of fixed speed, which depends on the physical structure. So, and this, by the way, called to another popular, so they have the design method which is based on an approach which I just thought that it's the opposite of what you usually do in control engineering. Because control engineer, you usually don't want limit cycle. No, so a natural dynamics which overlaps your what you really want the robot to do. In this case, you look for the limit cycle and you shape the limit cycle. So you let the robot do what it wants, and you intervene at the right point to control it. Actually, it is some people use it to say that a human walking is essentially a controlled fall. So I let my body fall, and then I take it at the right moment. What helps me with respect to this kind of rigid structure passive walker is that my structure can be deformed. And when I deform my structure, I change the speed, the limit cycle, and so I change the speed. And so the challenge is, and here I'd like to, the challenge is how I can develop from this standpoint a robot which is as good of the robot which has been so far developed by people working in what I could call the standard or mainstream paradigm, the mechatronic paradigm. So how I can go beyond mechatronics. So this is the problem, how I can really think to build a set of loosely coupled parallel processes to organize, to obtain behaviors, because the intuition says that if I have a self-organizing system, and the perception so is in some sense continuously recreated, I don't have the problem that I have suddenly a glass appear in my field of view, because I'm continuously recreating the worlds, so to speak. I'm continually self-organizing, and I have many parallel cognitive processes. So the idea is this, part of the idea is this one. The other point is that actually I save a lot of computing power because I use the passivity, so I don't have any control when I do it. So if I take take this point of a laptop, first I have a fall, and then I close my hands, but also my fingers, first they fall around, and only at the very last moment I close it. So I consume very little energy. And here, and also very little computation. I do very little computation. And here we have a big hint on the fact that, okay, but if you think to a mouse, it has several millions of neurons. No? So the mouse, which is probably not designed, has evolved according to this principle, has much more computing power than what we put in Asimov. So it's not, that's why the comparison is unfair, because on one side I have something designed to save energy and save computing power, which on top of that use an enormous amount of computing power. So it seems that really we are missing something. And the rest of my talk, which is actually is even more personal, because so far I have essentially described a paradigm view which is shared by, for instance, actually comes from people like Rolf Pfeiffer, but it's also shared by people like Kuniyoshi, Azada. So there is, let's say, a current in the community which share this view. Now I'm going a bit more in detail. So, and this is already a partisan point of view, but I believe has very good arguments, at least at conceptual, from an analysis standpoint, the arguments are very strong. The weakness of this approach is that if tomorrow you want to build a robot for doing some nice entertainment in a shopping mall, you have to follow the standard paradigm, because the mathematical models to implement the new paradigm are embryonic. So this is something that has happened many times in the history of technology or science, so that you have to choose between a stable paradigm which works like the Ptolemaic astronomy was extremely effective in explaining the movement of the stars. There were just 5 stars which didn't fit in the model. And if you think retrospectively, it was really bold to throw away all the model because it didn't explain 5 stars, no, the planets, no, no, there were some stars in the sky which were not following the model. And it took a lot of time to develop. We are, like in many other situations, in front of a difficult choice, because I could say, I don't know how to do it, so I won't do it. The alternative approach, okay, let's try to see what we can do. And here we enter what we could do. No? Because then you also have another subtle issues that you say, okay, robotics is essentially mechanical engineering plus electronics plus software engineering plus system engineering. Again, if I put enough stuff, I will get what I want. On the other side, I think we are missing really how this blending of capacity, so how I decide in my brain that something is computed and something is just made by letting the arm fall, how I can shape such a controller. So what is called an orchestrating controller, not a top-down, so a controller which essentially intervenes at some specific point to just guide and orient what would happen naturally, you know, the idea of a controlled fall. So how I can do it. So, and here there is a rhetorical question: does robotics need a paradigm change? I think it does require a paradigm change, and it's not. It's not, so I repeat the concept that the real weakness of this position is that as soon as you talk and you discuss the principle, everybody, no, not everybody, but it's quite convinced. The problem is that we don't have a quantitative model. And the rest of the talk is about how to build this quantitative model. So my idea, and a few other people, is that a critical point in the way intelligence evolves, and this is a paper from Nungarel's, so from several years ago, is that actually what determines what drives the learning process is the capability to manage more information. So as the learning process proceeds, what happens is that the system is able to manage more information. In which sense? In the sense of being able to predict the input of a sensor when I do something. And what is interesting in this paper is that considering 3 different settings, so kind of humanoid robot in A1, kind of insect robot, quadruped insect robot in B2, and wheeled platform with a camera, what happens is that in all the 3 cases, what I get is that I have I put a neural network, but I probably could put everything inside. And what happens is that the information flow, which is a measure of information transmitted built on Shannon entropy, no? Is as a peak when the system is behaving properly. So I look at the system and say, now it does what you should do. And what happens is that I have this peak in the transfer information. So the idea, on the other side, if I look for how I could decide, think in terms of navigating a room, so how, which is essentially this problem, how I can say that quantitatively, because the problem is that when I go away from the good old approach, which is the one that I would use if tomorrow someone asked me to send a robot on Mars. if I depart from there, I'm a bit lost, and I have to introduce some new concept. A typical, for instance, how I can say that this room is more messy of another room. Again, an approach, the first approach that you can think of is to use again Shannon entropy, which means that essentially I consider how unexpected is the layout of a room. And this is a way to tell it. Essentially is a weighted summation of the probabilities of finding something. No? So we don't have time to enter in much details, but this is the idea. So we have this that is actually used routinely into the communication engineering, and we use it, for instance, to say, these mazes can be more or less messy. And nice to see that, for instance, this metric, which was introduced in a paper by Lamp and Shatila years ago also, it's bigger when intuitively I say this is more messy than this one, and so also this matrix grows. So it's a valid metric that I can use. So the idea is that on one side I have this is a super simplified environment, no? Because I'm trying to build the model. So I have two things. On one side my robot is good when manage a lot of information. And at this point, ideally I could say, okay, my robot manage 2 kilograms of information, no? So, and my environment is 1 kilogram of information, so I can compare the entropy of the two. I can say, this robot will be able to manage this situation. And consider that this is also in terms of benchmarking of intelligent system is an open issue, so we don't really know how to quantify the fact that a robot is more flexible and adaptive of another. The idea, and this is of course my idea, is that entropy could actually be a good matrix for this kind of things, no? Because allows to set a single number to this different situation. So because I could also have any of this situation could be, I could move again there, but more or less I would say, okay, they are already more or less the same group of squares, and they are varying more or less in the same way, and they are more or less spaced in the same way. This will end in a number which is similar. So I can put a very large number of situations under the same numeric umbrella, no? On the same way. And so this seems a very, and on the other side I can use the same matrix to say, so, and this led some research by Prof and others to say, okay, why we don't build this self-organization simply by maximizing this information gain that we have seen in Lungarella experiment. And here it's interesting to see that something has been done and it has worked. It works. Then we can have a weak and a strong form about this idea of information-driven self-organization, because the weak form is say, okay, this is a valuable method to build a self-organization of information inside a robot. No? Because the attractive of this approach is that it is generic. No? So I don't put anything, I just say to the system, maximize this metric in between sensor, and then the system can try different strategies. So it seems very general and power. So the weak form is to say, well, this is a good engineering principle to build an intelligent system. The strong form is the second one. I say, I think that in nature this maximization of information managed by the system is actually what drives evolution of the animals or of intelligent systems. No? And this is a strong form. Could be, of course, this is another topic. So this is topic for with people studying evolution of animals. No, but this is a very strong form. At least in this weak form, it makes sense to try this engineering approach. And nice enough, there is this Snakebot. So interesting enough, this Snakebot is a very simple simulator robot, which is a series of balls which are loosely connected with each other. And the control, so to speak, is the maximization of the predictive information, which is one of these metrics built on the Shannon entropy concept, in between sensors and actuators. So essentially, what is very nice in this simulated Crotalus is that it behaves like a real rattlesnake. So, and this emerges from what? Because the old way would be setting a list of behaviors that are in your mind and writing them in some symbolic structure inside the computer. Here there is nothing like that. There is just a maximizer of the algorithm that I calculate of the input time series of the sensor and the output time series of the actuator. This is, and so it's extremely, of course there is a long way from this rattlesnake behavior like a rattlesnake and a humanoid robot. Very long way there. But the principle seems to be promising. No? So this is again is quite typical. Or it could be, of course, when you propose a change of paradigm, you might be right or you might be wrong. If you until you think that you are right, you say, okay, but this seems promising, and you can build on it. Another aspect is that, for instance, in network physics, we have a lot of methods to say which kind of quantity and of information is managed, for instance, by a small scale network. So on the basis of a different network, we can actually characterize again. So the idea is that I put together this with the other concept, this idea from network physics, I put together with this idea of information-driven self-organization, and I try to see what happens. This could be a way to try to implement something which is super simple in comparison to the natural example, but could be in the same line I can use the word design, assuming that we don't know, we don't believe it was some intelligent designer, no? But it's true that there are principles that have emerged and have been validated by the evolutions, by a natural evolution, which are clearly different from what we do. And the idea, let's try to do like nature. And so, yeah, I could be, of course, it's beyond the purpose of what we are saying now to go in the real technical details. But it's interesting to notice that, for instance, as regards the modeling of control system, an approach inspired by communication theory, which actually was developed almost alone by Charles Shannon in the 40s, has been applied to the problem of control, this approach of information-based approach to control system, only very recently. So this is a paper from about 10 years ago, and actually it was in the context of controlling quantum computing. So I'm not so surprised that, since they had to manage an intrinsically stochastic system, they had to refer to something like this, because you cannot really control the quantum system. No? So because it's not in the deterministic sense that we use for macroscopic. But apart from that, so what is attractive from this perspective is that, okay, so I'm actually developing a control system that I want to emerge and I want that it emerges on the basis of an information metric. At this point I have to browse the literature and to find that if someone did something like that. Luckily there is this approach coming from Touchet and Lloyd, which allows to do that. So at this point we see the different pieces of a puzzle. So I characterize the control system in terms of information following this approach. I maximize what is missing now here. I have a very complex environment, because if you think to again, if you look at nature, this is an approach coming from the epistemological approach to biology, no? Because I have many complicated things which depart from the standard good old engineer. No, I don't want to sound too dismissing, you know. So I mean, there is an approach which is actually but now I want to do some irony, you know? Where typically when this is not mine, it's from Dennett. No, Dennett says that when an engineer tells you that he is not interested in philosophy or epistemology, he actually means that he is a neo-positivist of the 19th century. So, and this is more or less the underlying approach that we have. So if we look at biology, we also have to enlarge a bit our perspective and consider, for instance, that we have causality at different level, and that the determination is very complicated. So it's a kind of stochastic relation by a number of roles which are concurrently operating, and a number of, again, stochastically distributed initial conditions. And this will give you a distribution on the... This, by the way, is an approach for coming from the epistemology of biology, which seems to maybe fit better to robotics, because since it is a product of human techniques, it's much simpler, and so it can fit to this kind of model. But what is missing, apart from this, what is really missing now? Because now I have linked the information, I have invented, I have inspired by nature, I have introduced a mechanism for self-organization of what? Of behavior, of control parameter. I have not told anything about the embodiment, because I was saying, so how I do this? This means that as I proposed now, this approach is limited, because still I don't consider the fact that I'm still working with numbers. And if you look at attempts, for instance, there was an attempt that I quoted before of using this information matrix-based self-organizing process. What you see is that they are extremely computing intensive. No, this doesn't seem very good. The idea is that if you, this is even more personal as an idea, is that actually, if you calculate these quantities not in the abstract space of numbers, no? So the vector space of all the possible values that a joint angle can take, but in the specific space of the possible mobility of the given mechanical structure, actually the problem in terms of computing complexity collapses. Here there is another price which is similar to the other one, because the other one was let's use a fancy, an unusual approach to control, characterization. Here the cost is, no, you cannot work in the usual Cartesian Euclidean space. No, you have to use Lie groups, and essentially to study the problem in a curved space. This has so it's as usual. You have a price. The price is that it is much more abstract, and so you have a level of abstraction. So the treatment of the problem at this point is information-driven self-organization, which is an abstract concept. On what? On an abstract space, which is the Lie group characterization of the mobility of your actual system. But at this point, what I have a system which self-organizes and is feasible in terms of computing power. So what I now, by necessity, I have described in short, is actually being detailed more in a number of publications over the years, so from some very actually preliminary to some more recent work. Some of it is still not published, but for instance in this paper on artificial life of last year, I actually described how this machinery of Lie groups description of a structure can be merged with an information-driven self-organization system. Of course, what we still have to do is whether this approach put on some maybe at least configure to a structure which is at least made of a rigid body which are loosely connected, or even better to a soft structure, can really work experimentally, because so far we have simulated, we have calculated, we have demonstrated that the algorithms are feasible, but we miss the really experimental approach. The excursus before on the epistemology of biology was we miss a serious experimental methodology for the whole robotics. So we have serious difficulties to say if a robot is good when good means able to manage uncertainty. So we don't know very well how to do. And this is a joke. I promise to come back on this because this is where we are. So actually, if we have a man or a woman hidden in the machine, making the processing the high-level cognitive issues, we can build the robot. And if you think about this, is what Da Vinci and opportunity and spirit have in common. So they work because the people who think, so it's not the system who thinks, is not the robot. The robot do something as a limited level of autonomy, and this can work. When we go to autonomous behaviors, we are in trouble because typically our robot works most of the time, but at some point I just move something and it stops to work. It's quite common to see that most of when you have seen, I suppose, as people interested in robotics, many demos. What happens if you should also look at the students managing the demo. Usually they are stressed. And why they are usually stressed? Because if you want to do a simple demo of a robot hand grasping a bottle, you have to fine-tune a lot of parameters depending on are the curtains open or closed, and about which again it is morning or so. This means that what has been implemented so far is, of course, remarkable. So it's still, I say, but conceptually is like Aaron's Automatas or conceptually, but in practice the level of complexity of functionality is much bigger. But still you have this problem that you have to recalibrate, to recalculate, and what the hidden promises of this approach, or similar, because we don't know, I don't claim that this is the only or the best approach, or similar is to be able, so at this point the robot intelligence system is able to adapt to the fact that the light, so a cloud pass in front of the sun, because now we have this kind of problem. So your mobile robot is moving in this street, but suddenly a cloud obscures the sun or change the lighting condition, and your system is gone. No? And so this is, in a summary, so what we are looking for is to a deeply being inspired approach, which actually implements self-organization. My particular view on this is it has to be an information-driven self-organization, and it has to consider the embodiment. So the fact that a large part of the thinking is not real thinking, it's just letting the arm go down. No? And so there are many problems, and I told before, this is more a research program for the future than a series of results. That's why I at the beginning said this is a kind of position talk, because the results have still to come. If you believe in the paradigm change, you are convinced that they will come. If you don't, you say you are losing a lot of time. You should just add more computing power to it. And then, as a conclusion, if you are curious about this, the general framework of this approach to robotics and AI, which actually links, say that you cannot have AI without a body, you should check the Shanghai lectures, which are actually were started in Zurich, several by Zurich University, by Rolf Pfeiffer at Zurich University ago, and they are continuing. Actually, last year I managed this, and you can find really a much more diverse set of opinion on this by checking the Shanghai lecture website and maybe attending next year Shanghai lecture. And that's all. Thank you for listening.